Today we're going to discuss about bias compensation using diode. So what is the reason why we need to bias a circuit? We know that the Q point, that is the quiescent point, is something which is unstable. That is, with the change in temperature as well as inherent variations that is seen in a transistor can affect the position of Q point. It can slip back and forth. So there is a need to ensure that the Q point is stable throughout the circuit when it is worked upon. So in order to do that, we need to compensate the circuit. For that, we use a diode and various other devices. So now we'll be discussing about compensation technique. So it refers to the use of temperature sensitive devices such as diodes, transistors, thermistors, which provide compensating voltage and current to maintain the Q point stable. So in the first place, we would be discussing about diode compensation technique. Why are we using diode to compensate? And what are we compensating in that circuit? We are compensating for the rise or the change in the base emitter voltage that you see here. Before moving on to the diagram, I will give a brief introduction about what the circuit, that is the diode and emitter circuit, consists of and how a diode can be used to compensate for the change in VBE. Our diagram would consist of a voltage divider bias with bias compensation technique using a diode. Here there is a separate supply called VDD, which is the voltage of the diode, and the diode will be in the forward biased condition. Here care must be taken that the diode that we use as well as the transistor should be of the same material and type so that they will have the same temperature coefficient as the base to emitter voltage. What we see is that due to the rise in temperature or due to the change in temperature, there is delta VBE change in the base emitter voltage. Similarly, a delta VD change in the diode voltage. These changes will tend to cancel each other and hence their effect is nullified. Now let's move on to the derivation. So here this is the diagram. It's a common emitter circuit configuration. You see here this is the base terminal, this is the emitter, and this is the collector. Now VCC is the supply voltage of the collector part and RC is the resistor that's attached along. RB is the resistance across the base terminal, RE across the emitter terminal. Now VT that you see here, it is the supply, DC supply, and VD is the diode. RD is the resistance across the diode. Now let's apply KVL, that's Kirchhoff's voltage law, to this base circuit. Okay, so VT in the LHS is equal to IBRB plus VBE plus the whole of IB plus IC into RE. See, this is the emitter. The current that is flowing through this resistor RE will equal to the emitter current. Now we know that emitter current is equal to base current plus collector current. So base current plus collector current into RE minus VD. So that is the KVL equation, and rearranging which we get the required equation. Now let's consider the leakage current. Leakage current is ICEO since it's a common emitter configuration. Before we moved on further into the derivation, what really is a leakage current? So in simple words, it is the current that is usually measured when the transistor is in its off state. We have two kinds of transistors. Obviously, ideal transistors, which are non-existent, but for defining purposes, we take it, and we do know that they exhibit zero leakage current. But in the case of real transistors, they exhibit some kind of leakage current. The significance of this term is because the quality of a transistor as well as its capability when used in a circuit can be determined by knowing the leakage current that it produces. Then we have ICO or ICBO, which is the reverse saturation current. These two terms are the important ones that we're talking about here. Now, from the previous recordings, we know that IC, that's the collector current, is equal to beta IB plus ICEO. ICEO is the leakage current for common emitter configuration. And that leakage current is also equal to the whole of 1 plus beta into ICO, which is the reverse saturation current. That is the relation. Now, from this equation, we are isolating IB to the LHS and shifting all the other terms to the RHS. Now, substituting the value of IB in equation VT, we get it as IC by beta plus 1 plus beta the whole into ICO by beta the whole into RB plus RA plus ICRA plus VBE minus VD. Now, earlier in the equation, we saw that there is a term ICRA. In order to manipulate the equation, we will be multiplying beta to both the numerator and denominator of this term. And the rest of the equation is same as it is. Now VT is equal to, and we are taking out the common terms IC by beta, and we get this term. Now we are shifting this term to the LHS, and VT and the rest of the terms are shifted to the RHS, thereby isolating IC. IC alone is kept in the LHS and all the other terms. Now, why are we doing this? Here, our intention is to prove that the change or the variation in VBE due to the temperature changes is not affecting the collector current anymore because we have used a bias compensation technique using diode. Here the term VBE minus VD, because of which there is a nullification as we had discussed earlier. Delta VBE is equal and opposite to delta VD, hence the change gets nullified and hence the circuit is biased and compensated for. So that's the end of bias compensation technique using diode. Now next we move on to diode and voltage divider circuit. So here a diode is used to compensate for the changes in VBE. There is a diode that is attached in series with the resistance R2 in the voltage divider circuit, and the diode is in the forward biased condition. This is another resistor R1. Then we have RC connected to the collector terminal, RE connected to the emitter terminal, and this is VB, that is VE, and VCC is the output terminal. Now let's move on to the derivation part. For voltage divider bias, from the diagram we know that IE is equal to VB minus VBE by RE. If you were to apply KVL for that small loop, you will get this equation. Now VB minus VBE is equal to VE. Now that is also a part in the diagram. If you observe, you will understand that. And then IE is equal to VE by R. Now we know that collector current is approximately equal to the emitter current. So IE is equal to IC, and hence the above equation can be rewritten as VB minus VBE by RE. To cancel the changes in IC, one diode is used in the circuit for compensation. And the voltage at the base VB is given as VB is equal to VR2 plus VD. Now substituting this value in the equation, in the above equation of IC, we get this term. VR2 plus VD minus VBE by RN. Now, from the previous case of diode compensation technique, we know that delta VBE is opposite to the change in diode, and hence it will get nullified. So the equation can be further rewritten as IC is approximately equal to VR2 by RN. So now we have once again proved that the changes in the base emitter voltage due to the temperature variations are compensated by the changes in diode voltage. That is, it is irrespective of the change in the base emitter voltage, the collector current remains the same, and hence subsequently the Q point also remains the same. And that was the intention, which is now fulfilled. Now moving on to the last section, which is the compensation for ICO. Here we'll be discussing about germanium transistor. So in a germanium transistor, changes in ICO with temperature plays an important role in the collector current stability. So the diode is kept at reverse bias condition, so only the leakage current flows. Now, when IO increases, we also know that ICO would also increase. Moving on to the next slide. Now let's move on to the diode compensation for a germanium transistor. So this is the circuit diagram for the diode compensation. Applying KVL on the circuit, we get that I is equal to VCC minus VBE by R1. And we know that this I is equal to IB plus this current IO. Now we can isolate IB alone and we would get I minus IO. For germanium transistor, we do know that the base emitter voltage is very small and insignificant. It is only in the range of 0.2 volt. So we can restate the equation I as we can neglect VBE, so it would become VCC by R1 approximately, which is a constant. Now we already know from the previous statements that IC is equal to beta IB plus the whole of 1 plus beta ICO. Now substituting this value in the above equation for IB, we would get it as IC is equal to beta I minus beta IO plus the whole of 1 plus beta ICO. And now this beta, if it's very much greater than 1, then 1 plus beta is still beta. So we can rewrite the equation as beta I minus beta IO plus beta ICO. Now if IO is equal to ICO, then we get it as IC is equal to beta I. From this equation, we have derived or we have concluded that as I is constant, IC would also remain constant. So any change in ICO with the temperature are being compensated by diode, and collector current will remain constant for a germanium transistor. That's the end of the discussion for a diode compensation technique. Thank you all.